In this video, we're going to take a look at an introduction to Series AC RLC circuits. And the items we're going to look at within each one are, well, we're going to look at resistors in series. We're also going to look at inductors in series, capacitors in series, and then finally what we're going to focus on is some of the definitions, the physical attributes, the rules associated with these types of circuits, the equations and calculations, which I hope will simplify the content in a better way than what your binder resource does. And then finally, a phasor representation of each one. How are we representing these on a phasor diagram? So let's get started. First one we're going to start with here is resistance. And resistance, we know, has a calculation that we can easily do to determine the total amount of resistance that a object possesses. So resistance, R is equal to KL. Remember, K is the K value or constant of resistivity, length divided by A, the area. It's a physical property. We show it like this, a resistor, and we measure it in ohms. What else is important is the definition. Resistance is defined as the opposition to current flow. So when we start looking at a circuit like this, a series circuit where we have R1, R2, R3, all four of these equations should be correct. All of these, right? We already know series rules, V1, V2, V3, I1, I2, I3, R1, R2, R3, P1, P2, P3. Good. If they were all 20 ohms, if they were each 20 ohms, and we had a source voltage of 120 volts, then we'd be able to work out all of the individual items, right? So let's look at some of the equations that would be utilized with this type of circuit. The equations that we have are ones that we have looked at in the past before. We've got I is equal to E over ohms, right? So the total ohms, we've got E times I would give me power, I squared times ohm would give me power, and E squared over ohm would give me power. And the reason it gives me power is because this is a resistive circuit. It is a resistive circuit. So very quickly, we would have then an R total of 60 ohms, an I total then of 2 amps. And if we wanted to calculate the voltage across each one of these resistances, because they were equal, all we'd be doing is taking the source voltage and dividing it by 3. So I'm going to say each V is equal to 40 volts. Now, what about the amount of power? The amount of power that each one would be consuming, well, we could take 40 times 2, and that would give me 80 watts, right? So each of the resistors will have 40 volts across it, and each of them will be consuming 80 watts. So I'm going to put all this info up. Each 40 volts, and each 80 watts. Okay, so how can we represent this information in a phasor diagram? Well, a phasor diagram, when we're looking at a series circuit, a phasor diagram needs to have a common reference. And the common reference in series is the one property that is the same for all of the components in the circuit. So if this is my circuit, it doesn't really matter what the components are that are in the circuit. We need an electrical value that would be the same for all three of these objects, and that would be the current value. So the way that a phasor diagram will work is we need to have a Cartesian plane. And then in addition to that, we are then going to start scribbling in our different phasors. Now remember, for resistive, what's the one thing we remember from resistive? Resistive means that the items we are going to discuss are in phase. They are in phase. So let's first start on our Cartesian plane by sketching our current value. I'm not using any scales, and so because of that, it won't be crazy accurate visually, but I'm going to draw the current here. And I've got 3 diagrams, and the reason I've got 3 diagrams, I'm going to try to sketch these so they're the same. Oh goodness, I really didn't do a good job of that, did I? That one looks shorter, longer. I'll do a better job in the future ones. This one here, this is I total, and that's equal to 2 amps. I'm sketching 3 Cartesian planes because what we're going to do is prove what's happening with the voltages by adding them together for each of the 3 resistors. So this is R1, R2, and R3. So remember, what did we say about voltages and currents of a resistive device? Of a resistive device, that means the voltage is in phase. So that would mean that my voltage, remember it's an open arrow, would be in phase with the current for all 3 of these. It's going to overlap. And so what I have here is V1 is equal to, how many volts did we calculate? 40. 40 volts, and we know that it needs to have an angle as well. I mean, really, this one also has an angle. Man, that's a brutal 4. There we go. At 0 degrees. And the total current is 2 amps at 0 degrees. The next one is V2, which is also 40 volts at 0 degrees. And the third one here is V3, 40 volts at 0 degrees. So if we were to add these 3 voltage phasors together, we could use an HV table, or we could use our mode 3, right? Adding them together with an HV table or mode 3. And what are we going to end up with? Well, the voltage value we're going to see on our Cartesian plane down here, this is going to be the sum of all of my voltages. It's much longer, and this is E total, which is 120 volts at 0 degrees. What is the value of current at this point? Well, it's the same as it always has been. It is 2 amps at 0 degrees. So when we're referring to a phasor diagram with resistance, we've got AC phasor diagrams with resistance. I've got the voltage, it's in phase with the current. Voltage in phase with the current, in phase, which we refer to in phase here. If we wanted to build a triangle for this particular circuit, it would look like a horizontal line because there is no reactive component. Try building an impedance triangle. Impedance triangle would look like this. And that's because there's no vertical. A power triangle would look like this also, horizontal. And so what that means is that the resistance and the impedance would be exactly the same value. And when we look at S, the apparent power and the true power, those two would be exactly the same, wouldn't they? And so if these are the same, remember our power factor is equivalent to the horizontal component divided by the hypotenuse. And the horizontal component that we're looking at is always the adjacent side. So I'm going to say power factor is equal to the in phase component, which is our adjacent, divided by the hypotenuse. What does that give me? Well, in a purely resistive AC circuit, the power factor then equals 1. What's the total power of this particular circuit? Well, it's going to be 80 watts multiplied by 3. 80 watts times 3 is 240 watts. Since there's no reactive component, the S also is 240 VA. And because of that, the in phase divided by the hypotenuse gives me a power factor of 1. We'll never get a power factor larger than 1. Power factor can go all the way up to 1, but it cannot exceed 1. And we're going to see that. These are 3 extremes that we're going to be looking at: resistive, inductive, and capacitive. All right, so let's take a look then at a different circuit, and that's an inductive circuit. So let's look at inductance. Inductance. Inductance is L. L is calculated as N squared mu A over L, which is a number of turns, the permeability of the core, the area of the core, and the length of the magnetic field. And this we would define as a physical calculation to determine what? The Henrys, H. And we indicated an inductor in this way, right? So inductance is a reactive component, and what that means is that when we put it into an AC circuit, it reacts different than a DC circuit. In a resistive circuit, it reacts the same in both DC and AC. So in an inductive AC circuit, the definition for an inductor would then be the opposition to a change in current flow. And so we have a few rules that would be associated with this type of circuit. We have series rules, and notice the series rules look eerily similar to what we had before for a resistive circuit. E total is equal to each of these added together. If we had all inductors, current's the same, the ohms added together, and then Q, remember we don't have any power, we only have Q. And Q is reactive power, Q1 plus Q2 plus Q3. Okay, so what equations then can we use to calculate some of these values? Notice how simplistic they are in comparison to the resistive. And that's what I want you to understand about this process. Ohm's law does not change as soon as we get into AC or as soon as we get into inductive circuits. The voltage divided by the ohms should equal the current. How about the equations for reactive power? Notice the voltage times the current of an inductor renders the vars of the inductor. The current squared through an inductor multiplied by the ohms of the inductor equal the vars of the inductor. So it's important to understand that if I take individual values of current and voltage across an inductor, by applying these rules, all I have to keep in mind is that rather than watts of power being calculated, I'm calculating vars of inductive reactive power. So if, again, each one of these inductors had an inductive reactance of, let's say, 20 ohms. Let's say each one was 20 ohms. 20 ohms of inductive reactance. Then the voltage, let's say the voltage is exactly the same as the last example, 120 volts, would that then mean that the voltage across each of my inductors would be 40 volts? And the power reactive that would be stored and released by each inductor would be 80 VARs. And then finally, the total current would still be 2 amps. So hold on to that, because we're now going to take a look at what happens with an inductive AC phasor diagram. So here's my inductive AC phasor diagram. Now, what did we say before? When we're doing series phasor diagrams require a reference. And what is the same in that series circuit? Well, the one item that's the same would be the current, wouldn't it? So between all three of these inductors, the property that remains the same would be the current. So let's sketch in the current. I'm going to try to make these a little bit more accurate this time, as in the same distance or length, because we know the length is representing the magnitude of the current. So this is I total, 2 amps at 0 degrees. If we wanted to sketch each one of the voltage values onto these three diagrams, we know they're going to be 40 volts, but where are they going to be placed? This is considered an out-of-phase circuit. And what we need to remember is that it is out of phase by exactly 90 degrees. And that means that the voltage and the current are out of phase by 90 degrees. You have a choice. We can either put the voltage down here, or we can put the voltage up here. Both of those would be 90 degrees worth of out of phase relationship, right? In an inductive circuit, it's always 90 degrees out of phase, but the current is always lagging the voltage. So in an inductive circuit, the current, I, lags the voltage. The current lags the voltage. So if the current lags the voltage, I'm going to put a little box around that because that's pretty important stuff there. 90 degrees, I lags E. I representing current, lags E, voltage. E represents voltage. If we want the current to lag the voltage, we then need to know what direction does time represent on this diagram, right? And so the direction of which these arrows are moving is actually in a counterclockwise direction. And so once we know that, what we're looking at trying to identify is if I were to sketch a phasor down here and rotate both phasors around the diagram, like you've seen in countless animations before, which of the two phasors would cross the finish line first? And that would be the current. We don't want that. We want the current to cross the finish line second. And because of that, it means that the voltage on a series inductive AC circuit will be shown up here. Now remember, they're all the same voltage. They're all 40 volts. They're all 40 volts. So we've got V1, 40 volts at 90 degrees. V2, 40 volts at 90 degrees. And V3, 40 volts at 90 degrees. So if we were to discuss the adding of the voltages, these three phasors to get the total voltage here, again, what we're attempting to do is to verify what the value of adding all of these vertical components are. Remember, we're proving Kirchhoff's voltage law. Kirchhoff's voltage law is what we're attempting to validate here. And we know in Kirchhoff's voltage law, all the voltages should add up to equal the sum. So how would we add these? Either an HV table or mode 3 on your calculator. HV table or mode 3. When we add those three together, what we end up with is a total voltage value, which is the sum of those three. E total is equal to 120 volts at 90 degrees. And where's our current value? Well, our current would be down here. And it still remains at 2 amps at 0 degrees. So in an inductive series AC circuit, the current would lag the voltage. What would my impedance triangle look like for this particular circuit? An impedance triangle, what would that look like? Well, since there are no horizontal components in this circuit, my impedance triangle would look like a vertical line. We would have XL, and that would be equal to the impedance. What about a power triangle? A power triangle, again, would have a vertical component, and that would be Q. And since there's no horizontal or power, then the S, the VA, would be equivalent to the Q of the circuit. And so again, if we were to calculate what the power factor is of this circuit, remember, power factor is always the adjacent side, which is the in-phase component, divided by the hypotenuse. What is the in-phase component value as a magnitude? It's 0. What's 0 divided by the hypotenuse? Remember, the hypotenuse is the total. Well, you could take the total value of your VARs, and remember, there is 80 VARs each. So that would mean 240 VARs. So in-phase component 0 divided by 240 would give me a power factor of 0. So this would be considered a lagging power factor of 0. And it's lagging because it's inductive. So every time we indicate a power factor, if it's not 1, then we have to indicate if it is lagging or leading. So inductive, it is always lagging. All right, so to review, impedance triangle of a purely inductive circuit, the XL would equal the Z, both of those being measured in ohms. A power triangle of a inductive AC circuit, the Q would equal the S. Q is VARs, S is VA. And then finally, power factor is the in-phase component divided by the hypotenuse of either one of these triangles. It doesn't matter. And the power factor would be 0 when we calculate it with our calculator. Put 0 and divide it by 240. You end up with 0. And we would identify that as a power factor of 0 lag. 0 lag. All right, so let's look at the last one. And the last one we're looking at is actually a capacitive circuit. So remember, capacitance, C is equal to EA over DI, which is E being the dielectric strength of the insulation between the plates, the area of the plates, and the distance between. It is a physical calculation for the construction of a capacitor. Cap looks like this, and it's measured in farads, which is an F. Much the same as inductors, AC circuits will have inductors react in a certain way, which we measure in ohms, XC. The definition then of a capacitor would be its opposition to a change in voltage. That is the definition of the characteristic of a capacitor. It will oppose a change in voltage. And so if we take a look at the individual circuit rules for this, series circuits, voltage 1, 2, 3, they add together. I1, 2, 3, good. What about this one? With XC1, C2, C3, that's ohms of capacitive reactance. And then Q, this would be capacitive reactive VARs, Q1, 2, 3. The calculations we have for such a circuit are the same yet again as what we have seen in the previous two examples. The current is equal to the E divided by the ohms. Q is equal to E times I. And remember, the voltage across a capacitor times the current through a capacitor would render this value of Q, and remember, VARs. Current squared times the capacitive reactance, and the voltage squared divided by the capacitive reactance. So just like the same two previous examples, I'm going to assign 120 volts to the source. I'm going to say each of our capacitors has a capacitive reactance of 20 ohms, and each of my capacitors would then have 40 volts measured across. And then finally, each of my capacitors would be storing and releasing 80 VARs worth of reactive power, which would then mean that the total current is 2 amps. So how is this going to be represented in a phasor diagram? Same process as before. What we're going to do is assign each one of these capacitors to its own diagram, C1, C2, C3, this being the total current, 2 amps. At 0 degrees, I'm going to try to draw them all the same length again. 2 amps at 0 degrees. And 2 amps at 0 degrees. What about the voltages? Well, just like in an inductive circuit, a capacitive circuit is considered to be out of phase. It is out of phase. So if it's out of phase, we need to know by how much. So I'm going to say out of phase. And in electrical physics in general, what we'll notice is that we have opposites. And so out of phase in a capacitive circuit, it is the same degree out of phase, 90 degrees. And what we're referring to is the voltage and the current. However, this time for capacitive AC circuits, the current value will lead the voltage. So in a capacitive circuit, the current value will lead the voltage for a AC capacitive circuit. So that means that my voltage values, instead of being in phase or being up here at 90 degrees, they're going to have to be positioned down. And these are positioned down at 270 degrees. Try to sketch them all the same. So what this leaves us with, V1 is 40 volts at 270 degrees. V2 is 40 volts at 270 degrees. And finally, V3 is 40 volts at 270 degrees. If we were to add these three voltage vectors together to prove Kirchhoff's voltage law, we would then find that our Cartesian plane should satisfy the requirement of what Kirchhoff first explained, which was that all the voltages in a closed loop should render the source value. And so when we do this, remember, HV table or mode 3, and all you're doing is you're adding 40 volts at 270 plus 40 volts at 270 plus 40 volts at 270, we end up with 120 volts. And that 120 volts is the source voltage, and it is, of course, at the same degrees. So E total is 120 volts at 270 degrees. So let's take a look then at the triangles. What sort of triangles could we have with a capacitive AC circuit? Well, what about an impedance triangle? Would it actually look like a triangle? With an impedance triangle, would there be a vertical component? Yes, for sure there would be. That vertical component would be our ohms of capacitive reactance. Now, there's no horizontal component, so that means that the third property of Z would have to be exactly the same as the XC. So the impedance and the XC would be identical. What about a power triangle? Well, a power triangle, same thing. What we would see is a vertical component, but that vertical component would be made up of Q, of VARs. And then what about the horizontal? There's zero horizontal, which means what would the VA or S be? The S would have to be exactly the same. And so what that means is that in the same way that we calculated the power factor of our inductive AC circuit, the power factor is still a calculation of the in-phase component of whichever triangle we want to use, divided by the total of that triangle. So it doesn't matter if I use the Z and my horizontal of 0, or I use my S and my horizontal of 0, the power factor we will get when you calculate it is 0. Now, what distinguishes a purely inductive circuit versus a purely capacitive circuit when it comes to the power factor? Because they're both 0. This is a pure capacitive AC circuit, 0. We distinguish this as leading. So leading will indicate for us that this is a capacitive circuit, 0 lead. So what have we then looked at for all of these different types of circuits? Well, we can display onto a Cartesian plane the values of each of the voltages, and we can display the values in a triangle. So remember, in series, we have current, which is always on the reference. We have voltages for resistance that are always in phase. So this would be where voltage values for resistors would be. So I'm going to say V resistors would always be at 0 degrees. Voltages for inductors, if it's a pure inductor, as in an inductor with only XL, no resistance. So I'm going to say inductor, and I'm going to put in brackets pure. as in there is no resistance, those will always be sketched at 90 degrees. And then finally, we have the voltage here, which is the voltage of a capacitor. And that is always sketched at 270 degrees. So at this point, you're probably asking yourself, good grief, why did we go through such a long process? I didn't actually have to use my HV table when I added all of these together, the inductors, to get 120. I didn't have to use my HV table to add all three of the resistors together to get 120. And neither did you really have to use an HV table to get your total voltage when we had three capacitors at 270 degrees. So why the heck are we learning this? Well, the reason is when we combine these values, when we combine resistance, inductive, and capacitive components into an AC circuit, we have to use a bit of our trig and Pythagoras in order to prove the concept of Kirchhoff's voltage law, and later, when we're doing parallel circuits, of Kirchhoff's current law. So I want you to consider that. I've got another presentation where I'm actually going to show you the outcome of placing an inductor, a resistor, and a capacitor in series, and we're going to see why this is so important, because we're going to get some really odd outcomes. So hopefully you will tune in to that.